Hello and welcome to Lecture 10. As you can see from the title slide, today we're talking about functional programming. Many of you are probably wondering, what do I mean about functional programming? I make programs that are correct, they're functional. I use functions in my programs. So functional programming refers to a particular set of ideas and philosophies and primitives. Don't worry. In this course, we're not a programming language in this course. We're not going to be too formal about it. Extremely informal, extremely hand-wavy. The reason why we're talking about it at all is remember the whole goals that we're talking about for Agile hard design flow, right? We had four themes for this course. Number one, close the loop as shown by our course logo. Number two, design for reuse. Number three, make tools do the work. And number four, design for readability. Turns out, for all four of those goals, if we do functional programming correctly, we can get a win, right? If we do functional programming correctly, we can make it more productive for us to write our code, so we can get our code written less time, close the loop earlier. Functional programming done correctly increases reuse, which is good. Also, making compiler do more work, make us do less work. That's what we want. Make tools do the work. And finally, if we use functional programming judiciously, and I'm going to essentially show you times where I go too far, it can be more readable, right? And so, like I said, there's a balance. I want some room for discussion as the lecture goes on about this. So for the next three lectures, which of course for those of you here in person, we spread over the next two lectures this week in person, um, we talk all about functional programming, how to apply it to Scala and Chisel, and we're very fortuitous this quarter where somehow lectures lined up where all three lectures happen to all fit perfectly in 1 week. So that's awesome. Okay, so what's when I say functional programming in this course, what am I talking about? You've actually already been seeing this notion of like, immutability and that kind of stuff. For today and this week, we're talking more about the notion of thinking about how to apply a function to a collection of elements, right? So rather than thinking about, sequence of steps to where you've been taught your entire careers how to program, thinking more about I have a bunch of things and how do I want these things to be transformed and how to do this in a way that's very regimented and constructed. And so that's what we say when we mean functional programming, or FP for short in this course, and that's what we're doing. To do that, we're going to cover a little bit of Scala as always, then cover some Chisel using the Scala and the classic back and forth. Um, so let's fire up a notebook. Cool, ready to go. So on that first slide, I tried to make that pitch, but more concretely, what are we trying to do, right? The whole point of Chisel is to make these reusable hardware generators, right? If you're writing straight line code, there's some benefit over Verilog, right? Stronger types, that kind of stuff. But the real power are these generators, right? Getting that reuse, right? We want to make these parameterized generators. And so, as we've seen in the last week and a half, 2 weeks, these generators are more than just having a simple, template for bit width, right? We can do things like actually change the internal topology, actually construct things pretty deliberately. We saw an example of a crossbar recently. And so these are all things working over collections. And so functions to work on collections are a great way to do that, right? And what we're going to see is that you know, any programming language is sufficiently general purpose. You can write anything in it, but if you're able to best have these features in the language to use them correctly, recognize there's certain patterns rather than kind of keep reinventing the wheel, actually reusing these patterns. It's not just less writing for us to write in this code, it's also actually more readable for someone else reading this code later on. So you can see this kind of throughout today and this week is how do we use functional programming to kind of recognize common patterns that are very abstract and then reuse them over and over again, right? And so as a developer trying to use these patterns, you may need to think of a problem a little bit differently in order to kind of get fit those abstractions, but it'll be worth it. It'll be good. And if we do it correctly, also can probably help us spot some of those errors too. Um, and, one little bit of advice I'll give you is that, uh, we've seen me pushing all quarter, try to use val rather than var, try to have, all this, immutable code and that kind of stuff. Chisel has some amount of intrinsic mutability, right? When you make that connection operator, you are changing those objects for that connection, right? Functional programming is intended to be side effect free, immutable, etc. But Chisel has some deliberate side effects, so be mindful of this distinction. And I'll show you today some examples of how to kind of convey that your code is going to have side effects rather than just being a pure function. Cool. So, why collections? As I said, we want to build these generators looking at end things, etc. Collections aggregate things that are similar to some extent. Um, so we want to use these to kind of pull it all together, right? Um, And so you may have seen in their languages, you're used to this, of course, as we have a collection of things, you're kind of using a for loop, and I'm going to do a for loop to do this, I'm going to do a for loop to do that, right? And so without thinking about it, you've kind of had a for loop with this pattern in your mind of how do I deal with end things, right? And it's very general. That's why it works so well. But we can do better, right? We can recognize some subtle nuances to handle that more cleanly, right? And so that's kind of the point. See, okay, every time you use that for loop, you're writing that same, perhaps in C, for int I equals 0. You're tired of writing that, etc. What can we do is better than that, right? So what are these patterns? How do we kind of use those patterns and make sure we actually follow those patterns? And probably can help us check those. So uh, how about that? This notion of parallel items. Well, the first two operators we're going to teach you are map and for each. We're teaching them you at the same time, side by side, right? So map, as the name suggests, is we're going to map, that is, apply a function to each element. So given some sort of collection of n things, I'm going to apply that function f element by element, right? And so yeah, so there's an input collection, output collection. This is a different collection, and you apply the function. Okay, sounds cool. So what's for each? For each applies the function to each element. There is no output collection. So that's a subtle difference. So wait a second, wait, they're both applying the function to each element, but for each has no output. So what does it do? Well, you use for each when there's some side effect of that function, right? For example, today's lecture is to see that side effect being printing to the console, right? Print line. But in Chisel, it might be doing a connection operation, right, which has a side effect. And so, if you're thinking about this from a simplicity point of view, you're probably thinking to yourself, wait a second. If they both apply a function to each element, and sometimes I want the output, sometimes I don't want the output, wouldn't map be in some ways more general? Because if I want the output, I have it. If I don't care about the output, I can just not look at it, and I can still apply the function, and that function could have a side effect. The answer is yes, that is technically possible, but discouraged, right? And the reason why is someone reading your code, they see map, they're thinking what matters from the map is the output. There shouldn't be side effects from this function. If someone receives for each, they're thinking some side effect is happening somewhere, right? So you kind of right away from that keyword telling them what's happening before you've even read the contents of your function. Okay, so let's actually play with some code. Before we do that, we got to be a little bit more formal, just for a second, about the functions we're using, right? So in particular, there's this notion of an anonymous function. You've seen these in a lot of languages, often called maybe lambdas, depending which language you're using. In Scala, they are called function literals. And what you do is they're basically a way of describing a function. In this case, let's say taking in an x, which is an int. Remember, Scala, the types go to the right, atypical. This little arrow operator, and then what the function does. So these are great for tiny little, one-line functions. There are ways to use braces and make this multi-line. If you find yourself in that situation, just write a traditional function. Okay, so maybe I'll kind of come some stuff out and start from the beginning. Okay, so we have our anonymous function, and it even tells you, yes, this is a function that takes an int and produces an int. Okay, yeah, so this adds one. Great. Now I can assign that to a name, like a val. So now inc, uh, is a val, the reference that points to this function literal, synonymous functions. So of course I can then invoke that function. Sure, great. That checks out. That's kind of what we expect would happen. So then there's a really subtle point, which for this course, the difference doesn't really matter. But if you're curious, wait a second. We've been defining functions like, this with def. Um, what's the difference, right? So one defines function, and the other one is a thing. And yeah, you can also call that, and there you go. So the answer is in this tiny simple example for this kind of simple one-liners, those two things are visibly, from the point of view of a programmer, equivalent. From programming languages semantics, are they equivalent? No, they're different. But does that distinction matter in this course? No. However, what I recommend? I recommend, yeah, if you're writing a function, use def. You can assign these anonymous functions to a val, totally legitimate. But oftentimes you don't need to. Often they're actually usually unnamed and anonymous mixed into an operator. You'll see that in a second. Now, what is the difference? This is creating, so val inc, this is a reference, whatever's on the right side equals sign. This is the function literal. Great. So in other words, this is evaluated, creates a function literal, and this points to it. What does this do? This defines a function. The function actually is re-evaluated. When you use def, it's actually evaluated anytime you do it, right? And so this is part of why you heard us before talking about avoiding side effects. If you have a side effect, with one of these, it'll happen every time you apply the function. One of these, it'll happen every time you use the function. So it's like a little bit different with a nuance. This is part of why I discourage side effects, right? um, and sure, you can have two argument functions. So if this distinction is confusing, don't worry about it. What matters about the slide is going to the syntax of arguments, arrow, function body. For simple short one-liners, you can have a couple arguments you need to. You can have a single argument. Boom. Cool. Questions? Yes. So depending on the way the function is written, of course, if you call a function, it's going to do the function body, right? But like, there's certain things that may exist inside of that body that will only get evaluated once versus every time. Like I said, this is one of these things where like, if you're in a situation where your code will work with val or def, but not the other, that's a pretty crazy situation. In this course, you can use probably one or the other interchangeably. I tend to think def is clear because oh yeah, I'm doing a function. Um, but this kind of shows you the power of having how the term they use is that these functions are first class, meaning that it's can be used anywhere, right? Yeah, so we're going to see some amazing one-liners today. Exactly right. So the reason why we're so excited about these function literals, we're going to see some amazing one-liners using these function literals like I've highlighted. And so usually these one-liners, we're going to have this literal be anonymous. So that the fact you bind to either a val or a def, you're not even going to see. And like I said, when you have a longer function you want to use, just write a def. You can have a def that's one line. You can write a two-line def. Sure, no problem, right? You can write a 10-line def, whatever you want. Um, yeah. Yes. If the return type is wrong, does the compiler report errors? It can and will. Let's see if we can make that happen. Um, so part of the challenge is going to be that in some cases, if you put a return type on things, it's going to cast, right? So like, can I do this? Okay, this one says no. This one says there's no return int into a string. So it's going to tell us no. Um, but the question is for function literal, how can I give this a type? I actually don't know. I'm going to try this. Is that how you give it a type? We'll find out. So then, yeah, okay. So yeah, so it can do that. The reason why, of course, I didn't have to label that type is because of type inference, right? Where int comes in, do a math operation on int, the result type is presumed to be an int. But yeah, as you suggested, hey, in the spirit of making compilers do the work, what if I put a type in there and make sure they match up? And so it's one of these things where if a type is what you would expect, I think it's better to leave it off. It's more clear and the inference is going to work. If there's a more complicated expression, yeah, using the type on both ends is a good way to make sure your code's speaking the same language of itself. Cool. Okay, so then let's play around with map operator. So we're going back. Remember, map applies the function each element, and there's going to be an output collection. Okay, so how do we do map? Well, collection on the left, map, and then function on the right. So you may remember I mentioned this previously. These collections actually implement all these features. So map is not a feature of the Scala language. Map is a function implemented on almost every collection you've ever seen. And it just so happens that that way it's written is so consistent that it feels like a feature of the language. Really, it's a feature of the Scala standard library, right? Okay, so here we have an example, Windows Dev, it does +1. So how can we use it? Well, we can apply map in a variety of ways. We have a range just to get something to work with. We can, do a very deliberate syntax, makes it very obvious what we're doing, right? I'm calling map on the collection L, and inc is the argument, which is a function, right? Like I showed above, you can write it like this. I may be a bit biased to write things that way because I, many years ago learned Scheme, and Scheme is similar syntax, right? With spaces, and so to me that's very clear. And as I mentioned before, right, Scala has far enough, parsing that, it can infer a dot should go here, and it can infer that these are parents for an argument. So yeah, we'll kind of figure that out. Um, but to be honest, I actually read Scala style guides. I actually recommend the more explicit writing like this. And it's not because this is error prone. It's not. It's because there's been a huge push in Scala to make it more readable by programmers who don't know Scala. So the concern is that people that are reading Scala who don't know it are going to see syntax and get confused, and they want to improve the readability for people outside of Scala. And so people outside of Scala are often either Java or Python programmers. Things like Spark brought a lot of Python folks into Scala. So yeah, so they've kind of adopted language features from both of those languages to try to make it more like them. So yeah, so this is now to encourage syntax, just because you know even if you don't know Scala, you see, oh yeah, I'm calling a function map on L and ink is the argument. See if about that stuff. It's not as obvious, but you know, in the safety of our own homes, I will prefer to have this simpler syntax. Um, what else can you do? Well, you can, uh, of course, apply a function using map, and then here we're now giving that function we were talking about. Remember, spiffy one-liners. Here's that anonymous function. In this case, we're saying, hey, let's take in I and then call inc of I on it, right? So we're using this function here. This, of course, is a little bit redundant, right? We already have inc in the proper, form. It can take in an int and return an int. Alternatively, we can also write the literal directly right here. So there's no need to define anything separately. We take in an I, return I plus one. And notice how, there's no types in here because it's all being inferred. As a reminder, yeah, we started off as 0, 1, 2, 3, 4, and then we turned it into 1 through 5 with these different examples. Questions? Yes. Yeah, so why is type being inferred is the question. The answer is it'll infer whenever it can, right? So if you don't label a type, in order for it to compile it statically, this is not a dynamically interpreted language, it needs to have a type to compile it, right? So the compiler is going to go running through, and everything that's not labeled, it has to figure out type for. So it's going to try and infer the types. And if it can't figure it out, it's going to tell you. But if it can, it's going to do it for us. Yeah. Question. Okay, if I had point 0.5, is that going to change the type? What do people think? Let's kind of turn that around. Yeah, I think so too. Let's see what happens. Yeah, see, it does, right? So what happened was, yeah, the Scala type inference rules are such that, yeah, if I have a clearly decimal number and I interoperate with an int, that gets turned into a double, right? And so type inference figured it out. So then, of course, the question is, can I break this by saying, you know what, I really want you to give me an int? And it says no, because you're giving me a double and I don't know how to turn a double into int. I can, yeah, I even crashed the kernel. Look at me, good job. So I have to relaunch some things over here. But uh, yeah, I can do as uint, which will do an explicit rounding. But in terms of saying, hey, I'm giving you an int, it knows for sure this is definitely not an int. You need to call a conversion intentionally. So yeah, I can go ahead and I can definitely say that. Ooh, I guess I need to do rounding, and I forgot what it is, but I can hit the tab key and it'll remind me. Uh, oh, well, there we go. There we have dot round. Okay. Ta-da! A little painful and a little ugly, but we did it. Let me go ahead and get this notebook running again because I broke it. Um, as you've seen that, this Ammonite, which gives us the power of Scala in Jupiter, is a little bit brittle, and so when things go south, it goes south. Um, cool. So that was map, right? So remember, map was we have an output, right? We have this thing going in, comes out the other end, and then for each, of course, still applies the function to every element. So everything else we've learned applies. It's just there's no output collection, and the whole point is there is side effect this function has. So, like I said, a canonical side effect might be I want to print to the console. And so yeah, let's do that, right? And so yeah, I have this range and I'm saying, hey, print that to the console. Now, like I said before, right? In some ways, map seems more general. Could I use map for this? Yes, I could. Uh, and what happens? It still applies the function to each element, but then they get this, result, which is all empty because, the result of print line is unit. So the empty parentheses is what's called unit in Scala, which means, this is like a void, it's like a non-type, right? And so, yeah, I get an empty collection of non-types. So I get a collection that's not empty, full of these empty types, right? And so this isn't very useful. Like I said, so by using for each, not only am I not having this output nobody cares about, um, I'm also conveying the point of what this function I'm calling is going to be the side effect, right? So instead of being print line, imagine this being some function someone's writing through their code. Before you even see inside that function, you see for each, you know that the point of this thing is going to be the side effect. Cool. So let's try this out in Chisel. Um, so what's kind of nice is that before we talked about, oh yeah, there's Scala collections like Seek, and there's Chisel aggregates like Vec. More often than not, you're going to use Seek in this course, but sometimes, a few times, you're going to need Vec, sure. Guess what? Both of those collections implement these functional programming operators, right? So Seek, of course, being part of the Scala standard library, yes, of course it has map and for each. Vec is written in the Chisel library. They deliberately added map into it to make it look like the Scala map to make it kind of more seamless, right? So here's some, trivial examples. I would worry less about why and more about just recognizing here's the most concise way of using some of these features, right? So let's say, for example, I have this module that's really silly that just takes in a number of elements and a constant and gives you that many ports with that constant, right? Heaven knows why you need this. Okay, so first we do this with a Scala seek, right? So I have a seek events, right? Zero until no elements. We've seen that. Okay, so that's a range. Then I'm going to map those ints, these are Scala ints, into chisel uints, right? We've seen the .u syntax before. Cool. And then, so now I have a seek of uints. I'm going to connect each of those uints to the output. So what I'm going to do is take the output collection. This is now a chisel vec. I'm going to call for each and give it a Scala sequence, right? So chisel vec map or for each given a Scala collection. They interoperated there. And then for each of those elements is it iterates through them, one of them at a time. So each of those I'm labeling O in this case. I'm going to hook each of those to a constant. So the fact that there's, zeros through num elements doesn't really matter. What matters is that uh, we're kind of doing this. So seek of units is really kind of a little bit of a extra superfluous stuff. We're just kind of showing things put together, right? So, like I said, you can map things together. In this case, we're not even using either of these. We're actually just directly connecting this. This is kind of dead code, but I'm just showing you how, yeah, you can apply map to seek. You can apply for each and map to a Scala, chisel vec, no problem. Sure, two outputs a constant. We can have four. Still works. So, yeah, I mean, we've seen from trivial Scala. Now we're seeing trivial Chisel. In a minute, we're going to show you more sophisticated Chisel usages. But any questions so far? Yes. Could the range be in the same line as a map? Absolutely. So I could definitely do this, right? Also remember, of course, that neither of these lines is impacting this. But even if they were impacting it, that'll still be fair. That'll be fair game. Yeah, so the order of these arguments do matter, right? So this is the collection you're applying the operation to, then the operation, and then the function you're doing with that operation, right? And so, yeah, this is kind of reminding us what we're doing here. This is the pattern, right? The pattern is I have a collection of things, and I want to treat them all the same. I want them all to have this function applied to them. And so both map and for each let me do that. Map saves the output, for each does not. And for each implication, of course, is we want to see the side effect. But yeah, so the every collection you're doing this on needs to be first, and the function goes on the right. Cool. Okay, then how about tuples? So I'm covering tuples now because we're gonna use them in just a second. So we've kind of seen this before, and maybe a little bit more proper treatment. So a lot of languages have this construct. It's a way to put together things into a object, right? And this is rather than being like name fields like a Scala class, case class, chisel bundle, this is just, cool things put together. They do not need to be the same type. Typically they're heterogeneous, but there's no rule about that. So yeah, for a couple of things, two, three things, these are perfect, right? If you have 10 things, maybe you should use the class. But we'll see some examples in a second where we'll do two things, the tuple is really good. Um, it's also helpful sometimes maybe you have a function that wants to return two things. You can return that in a tuple and you can take those two things and separate them back out. And so what are kind of key details of a tuple? Number one, the members inside there aren't really named. So you can see in this example, I just kind of toss them together. There's no names. Um, you can grab them by field. That's totally legit. Oddly enough, the fields start numbering from one instead of zero. It's a Scala specific decision. I forgot the reasoning behind that, but they made that choice. Um, and let's say you have a tuple and you want to turn it back into individual items. If you have the exact same combination of things, it checks out. Now, let's say, for example, I added in a third thing. So complain because, oh, wait, I have a tuple that's of the form int, right? And the thing on the left is saying it wants three things, right? In this case, this is the Scala type inference system talking back to us. It's being very general, right? It's A, B, and C could all be different types. That's why they're T1, T2, T3. It doesn't know what types they are. It's trying to make them match up. And it's saying, wait a second, you asked for what needs to be three things. Could be three different types, could be three the same type, but potentially up to three types, and you only gave me two things, right? So that's not going to check out. But yeah, in the simple cases, I just want to put two things together. Um, it works. Like I said, so you'll see some examples in a second of when this works great. Two or three things. When we start getting bigger, we've seen that, right? We like case classes. They're nice to handle a lot of things. The fields are named. You can add functions to it. It's great. In Chisel, we like bundles. And so Scala tuples, yeah, use sparingly up to a certain number of fields. Cool. Okay, so what am I going to do with these? There's an operation called zip. So what is zip? Let's go forward a slide. So given our input collection, so let's say input dot zip and then argument is a second collection. What's it going to do? It's going to go through element by element and pair them together, meaning that where I had two independent collections, now I have one collection where each element is itself a tuple, a pair that has an element from each collection. This is really helpful sometimes. So pairs of elements, you can join them together. And so where this comes up is very often, you can kind of see how this fits together, where we had this map pattern a second ago, and map was I apply a function to each element. And the answer is, well the question might be, well, what happens if I want to have a function and I want to apply it to an element from one collection and an element in another collection at the same time, right? I want to take, an element from collection A and an element from collection B and put them together in some sort of function. And well, if these two constructs, we can put them together, right? We can compose that operation, right? We can first zip the two collections together. So what was two separate elements are now one element joins the tuple, a pair specifically, and then I can apply map that actually have that function apply to that pair of things. So very commonly you'll see zip followed by map or for each is kind of a way to merge things together. So yeah, here's some trivial examples. So just to get a collection going, let's say 0 to 5. If I'll just do it one by one, right? If we run this, yeah, okay, we got 0 to 4, sure. Zip them together. Zip of itself, you're going to see, yeah, 0, 0, 1, 1. So these are two different, versions being zipped together. Sure. Now where it starts getting interesting, you may be wondering, wait a second, what if the collections that are zipping together aren't the same length? What am I going to do in that case? What if folks think should happen on this next line? L1 zip seek of 8. Seek of 8 is going to be only one element. Yeah, good suggestion. The suggestion was, I'm just going to take that first element and that's it. Absolutely. Yeah, because it can't go any farther. So you get the minimum of the two lengths, right? Um, Now, as I said a second ago, right? power to power, zip is often means zip followed by something like map or for each, right? So here we're taking these two things together. So it was, a set of elements. Now we have a set of pairs of elements, right? Great. Take map, and now I'm going to add them together. Um, so what we have, at this point, right? You can see this is a, seek, and the type isn't just int like we've seen in prior slides. So I go back a slide, right? Um, it's actually, oops, that one's not even evaluated. Uh-oh, what happened? Um, we see it's actually a pair, right? It's a tuple, right? Two ints. Great. Then um, now we need a function that takes two arguments, right? Because the tuple is sorry, tuple is one element. We want to kind of pull out those two fields. So yeah, we pull out the fields A and B like that. And so the reason why this case keyword pops up, this pops up a few times throughout Scala. It's a way to tell the language something called pattern matching. And basically the issue is, from the point of view of this map operation, each element that's being given is a single element, but it's actually a tuple inside. And so to kind of match up that tuple with A and B, you need that case keyword to tell it to try and do that pattern matching. And if you left that off, it should complain. And it's going to tell you, consider pattern matching, and yeah, put a case in there. I would have just been more direct in my terminology, like, did you forget a case? But yeah, but you can see what's happening, right? So zip, okay, we take two collections, pair them up element by element. If one of them is shorter, we stop prematurely. Usually it's helpful as a way to kind of join collections before applying something like map or for each. And so you can see already a handful of these operators, right? Things like map and zip, you can start building and composing surprisingly sophisticated pipelines, right? Um, these are all kind of simple patterns for kind of stitching together. Yes. Okay, good question. So how does this compare to the bolt connection operator in Chisel, which I'll write it out on the screen so people can remember? That's like this, right? I have, A bolt connect B. So the bolt connect operation in Chisel has some similarities, right? So the idea of that is, yeah, I have two collections. I'm going to go through one by one and connect them to the best of the ability. Now, the bolt connect operator has some flexibility, right? The things on the left and right don't need to be exactly the same type. They could be in different input-output directions, and it kind of figures it out. But I think you're right. If you were to kind of try to write this alternatively, you might say, oh, if I'm trying to implement bolt connect, which of course is not correct out of thing, I might say something like, oh, what if I zipped A and B, right? Like you were saying, and then okay, now I have this collection of tuples, and then I map them, and then I got to do connections. So let's say I want to do the connections, then uh, what's going to happen? Well, I'm going to have that tuple I got to match on first. So I'm choosing to kind of name these elements like that, and then so I would say this is in the same spirit as the bolt connect. It's not the same, right? Like I said, the bolt connect is smart enough to figure out when it goes through both sides, who's the input and who's the output. It's going to change on the left and right side of this connection operator if there's some smarts in there. But in spirit, yes, you can think of a zip and map, or I should say, actually, map tisk tisk should have been for each, right? Because the side effects of matters here. Map plus for each would have been, I guess, similar in spirit to the bolt connect for sure. Cool. Good question. Let's keep going. So this diagram keeps unrendering. I don't know why. Now let's try using these actually in Chisel. So in this case, we have another arbitrarily simple module, given a number of elements, and of course, a bit of why not. We're going to take in, I do not know why the kernel just died, but we're going to rebuild. Um, and then, as always, prime up the notebook. Great. Okay, back to here. Sure. So, given a vector of essence, so these are signed integers, we're going to apply the absolute value operation to all of them, right? So here's one way you might go about writing it. You could First, write this absolute value function. This is a Scala function that works on chisel objects. And what does it do? It uses the mux, right? If the thing you give me is less than zero, negate it. Otherwise, leave it alone. And so based on what you learned so far in this course, you'd probably write uh, something like this, right? And yeah, you could something like totally fine Verilog. You see it works out where it has the negative versions of each number and then uses the muxes to see do you get the negated version or not, right? Totally fine. Um, I think students also may ask, wait a second, well, why am I think sometimes iterating I through the range is helpful, but if you wanted to have perhaps no, actually, sorry, you need the I because you want to see both out and in at the same time. You need to kind of index in both of them, right? And so, yeah, so you need to kind of get the right input port and the right output port. So if I did this with the functional programming, oops, I would, of course, zip them together. And like you just saw, I have to do a case, I have an output port and input port, and yeah, connect the output to the input and I'm applying the function in between. And so, yeah, also works, so there's three lines turned into one line. I don't know if lines are the right um, metric, and I really don't understand why. So somewhere's causing hell. Okay, well then maybe I'll remove my sins. Actually, it still seems to be working, so we'll keep trying to go forward even though it keeps crashing. Um, cool. Uh, Questions? So yeah, so okay, we're doing for each, we're doing zip. Um, so you may have seen this before in the quarter, and now I'm actually going to tell you what was going on. So it's something called a placeholder, and it's a way to make these function literals even more concise. So rather than having to say arguments and then use it, I can have just the body. And the way it works is I use this underscore to be the argument. Now, the catch is, well, gee, what happens if I have more to one argument or more to one usage of that argument? The way it works is it goes in order, argument by argument, and every application of it is in order, right? So in other words, here it's trivial. There's only one argument. I only can use it once, but I only get to use it once. If I tried to say add to itself, it's gonna. Well, I'll do it correctly first, right? So I had zeros before, add one, sure. But now if I try to add it to itself, it's gonna yell at me because if I have two underscores here, that means this is expecting two arguments coming in, right? So it's like a single shot kind of usage, right? This is very constrained, but the times it helps, it's helpful. If this constraints are, not applicable in your case, just write it out. Um, and like I said, I've never used this with three arguments, right? I do it with either one or two arguments. We'll see some two arguments later today. Um, it is very concise. That's kind of nice. But yeah, cool. So we have that in our pocket. So then let's go back to our arbiter from last week. So we wrote a few versions of this. Forgetting the exact details of arbitration is fine. But remember what we had, right? We had a vec of inputs. They were decoupled, so we always raise invalids. We had a single output that was decoupled. And internally, we have these vecs because actually we are indexing into things. These aren't just seeks. And actually, they're wires because they're connecting them on both sides. For example, invalids, we declare. Then this for loop would go in and go ahead and connect it to each valid coming in on the input port. Okay. And then we later on use it here to make the output valid. And we do that by doing convert to a uint and then doing what's called an OR reduction, right? In other words, a bunch of OR gates to bring it down to one. Or take bits, for example. Once again, declare as a wire, connect it up in this for loop, and then now it's an argument to this mux1 hot. Mux1 hot, of course, this is selection signal, and this is the things it's choosing between. Um, so yeah, so this code wasn't our first draft, it was the second draft from last time. And the question is, can we do this better with functional programming? So let's see what we can do. So first, let's track invalids. Remember, invalids, we want to get the valid bit from all of our input ports. So we declared it there, and then we grabbed them all here one by one inside of a for loop. Well, we could just do that actually with map, right? In this case, it's map because we want the result, right? We want to go through all those input ports, map this function. What does it do? Well, using that placeholder syntax we just covered, say, hey, each string you give me, call dot valid on it, and put that in a collection, right? So now I have a collection of all the valids. So I think, and this is one of these cases where I would argue that functional programming is definitely helping us, right? We definitely went from, declaring a wire, iterating through it on the for loop, and now it's just, yeah, I want to grab those things. Oof, that's fast. That's clean. So I'm going to read that and understand exactly what you're doing. What else can we do? Well, uh, let's see. Can I go down the list? Now, like before, we had the out valid, and we still convert it to an or reduction, sure. Where else we use functional programming? We use it here for the um, bits. So if we go back a slide, remember bits I declared as, oh yeah, it's a wire, it's a vec. We go ahead and grab the field, and then we pass it into the mux. Here is an even more concise usage. I didn't even bother making a val for the bits. I actually just did it in place right here. The same thing, right? Applying map to the request ports, using that placeholder syntax, just, hey, everything you give me, call dot bits. So you can see in this case, I didn't even need to name it. It was just that concise. So you can really kind of collapse things. And then we have some logic about how do we want to do the ready signaling. So this is, remember, even though we're assigned this like it's an output, it came in and was kind of like an input. Because remember, these decouple things, that thing's going in both directions, right? So for every one of these ports, the ready field we want to set as the and of this chosen one hot. So whatever, is chosen, whatever that bit is, right? P, we want to pull out, and if the output is firing. So how do we kind of do that logic again? So here we did it as a for loop. Let's go all in on the functional programming. So I'm gonna go ahead and zip the IO request with the chosen one hot. And for each one of those, I'm going to take the IO side, which is the connection, okay, to dot ready. And then the chosen one hot, remember we did the zip, so that's kind of the two things. And then, okay, we then and these together with dot fire. So this is also correct. And so I think you now can kind of start to get maybe a little bit of your own opinion, right? Where I think things like grabbing fields out of a bundle, a vec, really clear when you get that right. So clear we didn't even bother naming it here. This time we're going to do a zip for each combo. This works, but I think it's a reasonable question to have or conversation to have. Okay, do I think this is more clear than this? And I think for some, I think the flow might be more clear, right? What's going on? So yeah, it's not, you're not always forced to use functional programming. Like I said, our goal is to build code that is not just correct, but more expressive and more readable. And I think you should definitely have that conversation in your head when you're writing your code about what makes the most sense to you, what looks more clear. I think this course is a nice kind of safe playground for you to try things out. Maybe try to push yourself on a homework or a lab to use functional programming constructs. And then when it comes time for your project, you can decide, do I want to keep using them or do I want to do things that are simpler? Because that way you can have a partner and you want to make sure you're on the same page and that kind of stuff. People often joke with the functional programming stuff that it's really easy to kind of chain it together. You can have, 2, 3 operators on a line. You get hooked and you can write it. And you come back and look at that code 6 months later, you're like, what is going on here? Right. And so, yeah, I recommend capping yourself to, one, at most two functional operators in a line. You can easily do 4 or 5, no problem, right? But that's not going to be easy to debug. So yeah, with some amount of hesitancy, right? Cool. Any other questions? Let